Hello. In a prior section, we just introduced the basic concepts and definitions of probability and counting. In today's topic, we look at a specific type of probability called conditional probability, when you are given an extra piece of information that might change your prior calculation, and then the role that that plays in what we call independent and dependent events. So to start, we'll work with a situation that might naturally lead you toward realizing when probabilities might change given a piece of information. So here's the situation. And again, you need to be a little familiar with cards and how many suits there are, and numbers and things like that. So situation, let's say you're playing poker and you're going for a flush in diamonds. A flush is when you get 5 cards of the same suit. So all hearts, all diamonds, all clubs, all spades. You already have the following 4 cards. So you have 4 diamonds already. You need 1 more diamond in order to get a flush. So the question is, as these are being dealt out, which is a better situation for you? You are dealt the next card, or your opponent is dealt first, so you're alternating, and then but you both have 4 cards already, and you see that your opponent then receives the jack of diamonds, and then you're going to be dealt the next card. So is it better if you were dealt the next card, or if you happen to notice that your opponent is dealt the jack of diamonds, and then you're dealt immediately after him or her? Well, situation A would clearly be better for you, because in situation B, you notice that your opponent was given a diamond and you need a diamond, and so there is 1 less diamond in the deck for you. So that extra piece of information automatically maybe makes you less confident that you're going to get a diamond because there's 1 less diamond in there. And that extra piece of information has now changed your confidence. In mathematics, we're really talking about that it's changed the probability that the card you are about to get then is going to be a diamond. And as I said, that is what we call conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred, given that you know some extra piece of information. And the way that we write this is we write this as the following. We write this as the probability, then in parentheses we put what has happened. We're asking the probability that B occurs, and then this vertical bar is the mathematical phrase given in this case. Given that event A has occurred. So the probability that B occurs given that A has already occurred. That's what we mean by conditional probability, given the condition that A has occurred. So here's an example. Let's say 2 cards are selected in sequence from a standard deck. Sequence meaning back to back. Find the probability that the second card is a queen given that the first card is a king. So 2 cards are being pulled out of a deck. What's the probability the second card is a queen given the first card is a king? Well, if I know the first card is a king, I really know that there is only going to be 51 cards left in the deck, and there are still 4 queens left in there. So there is a 4 out of 51 likelihood that the second card is going to be a queen given the first one is a king, because in a normal deck of cards there's a 52 cards and 4 queens, but 1 king has already been drawn. So 4 out of 51 chance. This is also used in what we call a two-way table, the idea of conditional probability. So the following table shows the results of a study in which researchers examined a child's IQ and the presence of a specific gene in the child. So this is kind of combining really almost a medical study with how it might affect intelligence or maybe learning styles and things like that. So first question just says, well, actually let's just kind of make sure we can read the table. So like, for example, just denoting the items in the table, this 33 means that there were 33 children where the gene was present and they had a high IQ. This 11 means there were 11 children where the gene was not present and they had a normal IQ. In total, there were 50 children that had normal IQ, 52 children that had a high IQ. There were 72 children that had the gene present, 30 children that did not have the gene present, and 102 children in the study. What's the probability that child has a high IQ? Well, we already said there's 52 children that have a high IQ, so 52 out of 102. If you want to simplify that in fraction, you can. I'm just going to get it to a decimal so I can relate it as a percentage. That turns out to be 0.51, which is about a 51% chance that child has a high IQ. What's the probability that child has a high IQ given the child has the gene? So the first one was just what's the probability of a high IQ. Now we're asking what's the probability a child has a high IQ given the child has the gene. Well, the reason that this is a different question is because this first one was all of the ways that they could have a high IQ, whether the gene was present or not. But now I know that the gene is present. So I know that my table is really shrunken down, and this is the only thing I'm going to consider because I know that the child has the gene present. So there are 72 cases where the gene is present. So it's out of 72 children. How many also have a high IQ? Well, 33 out of 72 children have the gene present and a high IQ, which turns out to be 45.8%, 0.0458, which goes to show that if you have this gene present, it looks like it lowers your odds of having a high IQ because in the general population, for all people, it's a 51% chance. But now, once I know that they have this gene, it lowers the likelihood that they have a high IQ, and that's why it might be of interest in a medical field. This is connected to a topic known as independent and dependent events because whether something has or has not happened may or may not change the likelihood of the second event. If it does not change the likelihood of the second event, then we say that those events are independent events, meaning free from affecting one another. So the occurrence of one event on the other does not affect the probability of that second one occurring. That means they're independent. We mathematically would say this: the probability of B given that A has occurred is just equal to the probability of B occurring in the first place because A had no effect on B. Or it could go the other way around. The probability A occurs given that B occurred is just equal to the probability A occurs in the first place because B has no effect on it. So events that are not independent are dependent. Dependent meaning that they did affect one another, and I have to consider their conditional probability. An example: decide whether the events are independent or dependent. So selecting a king from a standard deck, not replacing it, so you keep it, you don't put it back in the deck, and then selecting a queen from the deck. Well, I need to calculate the probability of, in this case, if it's B given A, the first thing occurring. So selecting a king from a deck, not replace it, and selecting a queen. So we want to find the probability of selecting a queen given a king first, and then we also want to find the probability of just drawing a queen in general and seeing if these two things are equal. If they are equal, then we're under this assumption that they are independent because it didn't have an effect. If they are not equal, then the fact that the king was drawn first does have an effect on the queen being drawn, and it means that those two things are dependent. So I calculate them. The probability that I get a queen given the first one is a king is 4 out of 51. This was actually one of the first example that we did. The likelihood of drawing a queen from the get-go, though, is 4 out of 52 because there's 52 cards that start in the deck, and you'll see that these two things are different values, so we see that these are dependent events. The fact that I draw a king first definitely has an effect on the probability of getting a queen second because there's one less card in the deck. So we'd say that those events are dependent. Just one more situation. Decide whether the events are independent or dependent. Tossing a coin and getting a head, then rolling a six-sided die and obtaining a six. So we're looking here, what's the probability of getting a head, or sorry, getting a six, probability, getting a six, given that the first thing that happened was I flipped a head, and see if that is equal to just the probability of getting a six from the get-go. And this is more of just a thought process. You kind of have to think through it. There's no mathematical real calculation that you do in this aspect over here on the left. I would hope you know the probability of getting a 6 on a six-sided die would be 1 out of 6. So really we need to ask, is the probability of getting a 6, given that the coin was flipped head, different than 1 out of 6? And it's not. The probability of rolling a 6, given that a head was flipped on the coin, the fact that the coin came up head should have no effect on the likelihood of getting a 6 for rolling a coin. So I see that these two events are equal. Because they are equal, the fact that getting a head occurred had no bearing on my likelihood of getting a 6 when I rolled the die. So those independents are free, those events are free from one another, which means we would say that they are independent. The head occurring had no effect on the likelihood of getting a 6. I'm going to give you a chance to try this idea. Going back to the situation of maybe a medical researcher comparing the effect of a gene being present on IQ. So find the probability that a child has a high IQ given that the child does not have the gene. also state whether these are dependent or independent events. So what's the probability that a child has a high IQ given the gene is not present? So no gene, which means gene's not present. Find that value and then ask yourself, is that value different than the probability of having a high IQ in the first place? If those two things are equal, then you'll say they're independent. If they are not equal, they are dependent. So pause the video now, give yourself a chance to try it, and then come back. Okay, let's see how you did. Probability of high IQ given no gene, so no gene present. What's a high IQ likelihood? Well, that's a 19 out of 30 likelihood, which is 63.3%. Probability of having a high IQ in the first place we did earlier was 51%. I see these two values are different from one another, so there's an effect of not having the gene. Actually, if you don't have the gene, there's a higher likelihood of you having a high IQ. That's why medical researchers might care about this, because so those are dependent events. The likelihood of having a high IQ depends on whether the gene is or is not present. Last thing that we're going to look at is something called the multiplication rule for the probability of A and B. So when you need to calculate the probability of two events occurring in sequence back to back, you can also use the multiplication rule for what we call these are compound events. Compound meaning multiple, so events occurring back to back. The probability that two events, A and B, will occur in sequence, the probability of A and B occurring is equal to the probability of A occurring in the first place times the probability of B given A has already occurred, because I already said A occurred in the first place. If the events are independent, then I know that probability of A given B is just going to be the probability of B, because A had no bearing on B occurring. So if it's just for independent events, I can take the probability of A, multiply it by the probability of B, and that will be the likelihood of A and B occurring back to back. And you can extend this for any number of events. So in this case, we're just doing 2, but you could do this for 3 or 4, however many events are occurring back to back. So we'll look at a situation where we can use this multiplication rule, simply multiplying event A times event B. Essentially, this is the multiplication rule we used for counting in the last lesson. We're just doing it for probabilities. Probability A times the probability of B. We just have to consider whether A had an effect on B. Here's like a kind of a lead-in about where this idea is used. This isn't in your notes. You can just kind of sit and maybe hang your hat on the idea. So this is actually used. I've kind of simplified it down to a scenario where we can kind of comprehend it. But search and rescue teams use this when they're searching for maybe a plane that went down in the ocean. The actual first thing they do is they search, they narrowed it down to the area where they think the plane might have went down, and then they search the area actually where they think the highest likelihood of survival would be, because that maximizes the odds of them finding them survived. So a search and rescue team believes there's a 40% chance a plane went down in the following area. What is the likelihood it went down in this area and landed in the forest? So I want to know what's the probability that it went down in the area and went down in the forest. So what do I need to do? Well, I need to find the probability it went down in the area and multiply it by the probability that it's in the forest, given that it went down in this area. Well, the probability that it went down in this area, we knew from the get-go, was 40%. And the probability that it went down in the forest, given that it's in this area, was 50%, because I can see the forest takes up 50% of the area. So 40% chance it went down in the area, and a 50% chance that it's in the forest, given that it's in this area. Well, 40% times 50%, 0.4 times 0.5 is 20%. So there's a 20% likelihood that it went down in the area and is in the forest. And that helps search and rescue teams know where to maximize their time when searching for down planes or anything like that. So that's where this idea gets used. Situations that our book will ask us to calculate are the following. So let's say the 2 cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. We've kind of done this. We've just done it in our head. So now we're going to see kind of how it plays out. Well, the probability of getting a king and a queen. Well, the probability of getting a king, off the bat is going to be a 4 out of 52 chance, multiplied by the probability of a queen, given that a king has already been drawn. Well, there are 4 queens in there, and given that a king has already been drawn, there's a 51 number of cards in the deck. So 4 out of 52 times 4 out of 51 is going to leave me with, well, 4 divided by 52 times 4 out of 51. If I multiply those two, I end up with 0.006, which as a percent is about a 0.6% chance of getting a king on the first draw and getting a queen on the second draw. Second situation, coin is tossed and the die is rolled. Find the probability of getting a head and then rolling a 6. So probability of getting a head and then rolling a 6. Well, I first need to find the probability of getting a head and then multiply it by the probability of getting a 6 given that a head has occurred. But we already did a second ago, noted that these are independent events, and since these are independent events, this is just going to be the probability of getting a 6 all on its own because the head has no effect on it. So I can just do them independently. So the probability of getting a head is a 50-50 chance, so 1/2 times the probability of getting a 6 is a 1 out of 6 chance. How do I multiply fractions? Numerators times numerators, denominators times denominators. I get a 1 out of 12 probability. 1 divided by 12 leaves me at 0.08 or 8% chance. This is also used in the medical field in terms of calculating maybe likelihood of successful surgeries if you complete so many in a day or in a row. So ACL surgeries are very common, especially for young people that are incredibly active. So the anterior cruciate ligament, the ACL, reconstructive surgery, has a probability of success for any individual surgery of 95% chance. So 95% chance any individual surgery is going to be successful, and it should be noted each surgery is independent from another surgery. Whether one was successful or not will have no effect on the next one being successful. Entirely complete different person. A doctor has 3 scheduled for the day. Find the probability that all 3 are successful. Well, because these are independent events, this is just going to be the probability of first success times the probability of the second success given the first was successful. Because these are independent, I can just write second one is a success times the probability the third is a success. The first is a success 95% of the time, second 95% of the time, and third 95% of the time. 0.95 times 0.95 times 0.95 tells us the likelihood of getting 3 successes all in a row is going to be 0.857, so approximately 86%, 85.7%. What's the likelihood that none are successful? So that'd be probability of 0 successes. That means the probability that the first is a failure, the second is a failure, the third is a failure. Well, I can kind of see what this is going to be. The likelihood the first is a failure is going to be 5%. Likelihood that the second one is going to be a failure is also 5%. And the likelihood that the last one is going to be a failure is also 5%. So I can just simply multiply them because they're all independent from one another. The fact that the first was a failure should have no effect on the second or the third being a failure. So this turns out to be 0.000125. Last one, probability at least one is successful. And this is where we're going to use an idea that we've did in a prior lesson called the complement. The probability of getting at least one success. That would mean the probability of getting one successes, exactly one successes, exactly 2 successes, or exactly 3 successes. I'd have to calculate 3 events in order to do that. So instead of finding all 3 of those events, I'm going to find the probability of getting the opposite. The opposite of at least one success would be 0 successes, and then I'll subtract that from 1 because that has to be what remains, because there's only 2 things that can happen. Either I get 0 successes or I get at least 1 success. If I find what the probability of 0 successes is, then the likelihood of getting at least 1 success would have to be the complement. But I actually found 0 successes in the last situation, 0.000125, so minus that from 1, 0.00125, tells me the likelihood of getting at least 1 success is going to be 0.999875. And that is how we can calculate at least 1 success. Last one, just to give you a chance to try these types of events. It says this: in the school, 21% of the students are seniors. Of the seniors, 52% are female. Find the probability that a randomly selected student from the entire population is a senior and a female. So just to give you a little bit of an idea of how that's going to work, you need to find the probability of them being a senior and a female, which would be the probability of a senior times the probability that they are a female given that they're a senior, and then you can multiply those two because these are compound events. And then similar situation for the male's case. So pause the video now, give yourself a chance to try. Okay, let's see how you did. The first one, we said there's 21% of the student population is seniors, and I want it to, for it to be female, given that they're a senior, and we know 52% of the senior population are females, so 21% times 52% leaves me at 10.9%. What's the likelihood that they're a senior and a male? Well, 21% again are senior. If 52% of the seniors are females, 48% have to be males, so 21% times 48% leaves me at 10.1%, and that is how I can calculate those compound events. That is it for today's topic. Thank you very much, and have a good day.